Thank you so much for having me back. Thank you to Sigma for hosting us in this beautiful space. I want to talk to you today about the paper that hopefully you had a chance to look over, and it's called Impossibility of Distributed Consensus with One Faulty Process, or as I like to call it, Far Apart Computers Are Hard. I work for a company called Pivotal. Pivotal is actually right up 6th Avenue, about 20 blocks north of here. I know we have a couple of former and current pivots in the audience, so hello, thank you for coming. One of the things I do at Pivotal is I get to work with large, complicated distributed systems, usually that are running in large, complicated distributed companies, and sometimes those large, complicated distributed systems were written by people 20, 30, 40 years ago. Some of them may not even be alive anymore, and the way that they're built is complicated. And the nature and the diversity of the kinds of systems that I see like that makes me really interested in the nature of distributed systems and what we know about them and what we've learned about them in the, say, 40, 50 years that we've been studying them from a computer science perspective. So I think this paper is especially interesting in that regard because it's so seminal to a lot of the work that came afterwards in how we understood distributed systems. And in order to understand that, it might help to set a little context about the environment in which the paper existed before we actually dig into the meat of the paper. So the year is 1978. I was not alive, and we were basically in the good place for distributed systems. Things were awesome. Like, we thought that we were starting to get a handle on what reliability meant and what it means for a system to do its job well when it's distributed. And this sort of era was characterized by a couple of different papers, but I think one of the most important was another paper called Time Clocks and the Ordering of Events in a Distributed System, which was written by a guy named Leslie Lamport, super famous in the computer science and distributed systems world. And the question that he asked in the paper is basically, can we assign a total ordering to the events received by multiple computers? If you have a bunch of servers or processors or whatever that are distributed, and they receive events of some kind, is there a way to impose a total ordering on those events as seen from across the system? Because each process might have a different idea of what the ordering of those events was from its own perspective. And that led to the idea of something called Lamport clocks. This was great. So a lot of people were very excited about Lamport clocks and the fact that you could sort of impose this serialization under certain conditions on this other, the fact that you can sort of impose order on chaos was, I think, very fulfilling and feels good from a science perspective, right? Because scientists love kind of imposing order on chaos and coming up with these universal laws that apply to everything, and they feel like they understand the universe a little bit better. But as famous distributed systems scientist Katy Perry once said, that you have to be careful about living in a bubble, because just because what you know now is true doesn't mean that it can't be upended by a broader, more expansive view of the world. And unfortunately, that's what happened in 1983 with this paper, Impossibility of Distributed Systems with One Faulty Process. It was authored by 3 different people, Michael Fisher, Jane Lynch, and Mike Patterson. The question they asked in their paper is, can you always come up with a way to get computers to agree to cooperate? Can you always have some situation, can you always have some protocol that decides the value that you're looking for according to some algorithm? And the answer, it turns out, brought us to the distributed systems bad place, because it turns out that this is not possible, as we'll see in this paper. And these 3 people were responsible for taking us to the distributed systems bad place. So I want to focus on the abstract of the paper because it gives us hints about what's going to come ahead, and I've omitted the last sentence here because it's not super important. So the first part is that we're talking about an asynchronous system of processes. So those are important words because those will form the backbone of how we think and talk about this system as we go through the proof. And specifically, some of the processes may be unreliable, and we'll talk about what unreliable means. And the problem is that we want the reliable processes, the ones that are not unreliable, to agree on a certain value. And the paper discusses how no matter what protocol you pick or design or invent, there's always the possibility of non-termination. It's always possible that your protocol could lead to an infinite run that does not decide a specific value, even if there's only one unreliable or faulty process. Welcome to distributed systems, specifically the distributed systems bad place. So this paper is complex in the sense of before you can even get to the proofs, you have to read about 37 different definitions of what things are, and you have to accept those definitions and understand them before you understand what it means for them to be used in the proof. So I'm going to try to simplify those 37, 40-ish different words into a few more condensed ideas that we'll refer back to. Let's first think about a node. And by node here, I mean something that can receive values. So it could be like a process, for example. And there's something that wants to send values to that node. We'll call it a client. The client wants to write a value, let's say. And the expected result of writing a value is that the node's internal state is updated to contain that value. Success. Later, we'd like to do something useful with that value. We'd like to read it out, perhaps, either by that client or by a different client. And so we'd like to get that same value back. We would not be happy with a read result that returned a different value than the one that we wrote. So that means, sort of importantly, the order in which we perform these operations matters. If we try to read before we've written anything, there's a problem, right? And specifically, the one operation that we're very interested in is if this node can make a decision about using the internal state, it's going to make some kind of decision. That decision could be what is the value itself. It could be take the value and multiply it by 2. It could be listen for the last 5 values I've heard and take the biggest one. There's some process or procedure or algorithm that it's going to apply to that internal state. So that's a case where we have one node. So we're not really distributed here. We're talking about one thing. We're not talking about n things. So we're talking about n things. What we would like is a world in which the n things kind of behave like one thing. That is, it should be transparent to the client. When they write a value, it should wind up somewhere, but the client shouldn't have to know the internal details of how that distributed system is organized in order to be able to subsequently read the value out, just like they did with the single node case. So in order to behave correctly in a world like that, we need some kind of operation. We need some kind of decision protocol that describes what the right value is given a sequence or a series of values. So if we imagine, say, getting 3 different writes for 1, 8, and 5, we're going to need to apply some kind of process or procedure here that decides what the correct value is. So if the protocol that we apply is pick the maximum value you've ever seen, that's the decision, great, then you would return a value of 8. If the protocol is pick the last value you saw, then great, the answer would be 5. If the protocol is pick the first value you saw, then the answer would be 1, and so on. So whatever algorithm you happen to pick for that decision procedure, you want it to apply to all nodes, and you want them to return the correct answer. So can we do that? Can we make a decision for a set of such nodes, not just one, but a set of them? So we really want the situation on the right to behave like the situation on the left, but we don't really have a situation on the left. We have a distributed cluster or arrangement of these different processes. And the way in which we decide to set up that arrangement, or the assumptions we make about that arrangement, will determine in large part what kinds of things we can say about the behavior of the system. And in lots of different distributed systems papers around this era, you'll see people sort of tackling the problem from different dimensions or different axes. And I want to talk about the specific model that the FLP authors used in their paper. So we'll start with what the idea or the FLP system looks like. And the 4 dimensions that we'll focus on are called processes, determinism, synchronicity, and failures. By processes, we mean what are the things that do work and how do they do it? How do they change their state? How do they move from one state to the next? What is the meaning of a state? What components go into the state? And so on and so forth. By determinism, we mean for some input, will the process always return the same answer? If I tell you 1, 5, and 8, and I have a process whose decision function is based on picking the maximum value, will it always return 8 given those inputs? Synchronicity means how long will we wait for messages when we transmit and receive them, and then what might happen in the transmission or receipt of those messages. Let's talk about processes first. So the way that the FLP processes work is that there are n processes, there are n things that can send and receive messages, as we'll see later. And those processes are arranged in a graph. And by graph, I mean the computer science meaning of the word graph. That is, there are vertices and edges that connect the vertices. And importantly, the graph does not have to be, has to be connected, but it does not have to be complete. Not every node has to be able to talk to every other node. It's okay that they communicate indirectly. So for a given process, for a specific process, P sub I, we want that process is going to have some kind of internal state, which I've called S here. And it also has two other important pieces of that state. One's called an input register, and one's called the output register. The input register is a value that only takes on 0 or 1. It's a single bit piece of memory, right? The output register can take on 0 or 1, or a special value that's undecided, which the paper calls B. So if you see a B, that means that no value has yet been written to the output register. And importantly, the output register is write once. Once a process puts something into the output register, it can't write to that output register again. That sort of represents the decision that the process has made, essentially. The way that the process changes its internal state is through a transition function, f sub I. So the process P sub I has a transition function, f sub I. These transition functions need not be the same for all processes. And the paper does not assume that they are. It's just important that they are known and well-defined. So the system, so that was a specific process. The system that the FLP paper considers is a world in which the state script P is defined by the collection, only the collection of input registers and the transition functions. It doesn't depend on anything else. And the system is completely specified by that initial configuration. All right, so how do processes send messages to each other? Because if they can't actually do anything, then they can never change state, and we have a very boring paper. So the way the paper defines it is that a message is a pair, P and M, where P represents the identity of the destination process that you're sending the message to. So if you say, want to send a message to process 3, then your P will be 3. The M represents some message that's in the alphabet or universe of all possible messages, and all that's important is that you specified what those possible messages are. There's another special global component called the message buffer, or what the paper calls the message buffer. And the way the processes send and receive messages is by asking the message buffer to send and receive messages on their behalf. There's not one message buffer for every process, it's one message buffer for all the processes together, so it's a global state, if you will. When you send a message, you tell it which process and which message you'd like to send, and the message buffer remembers that. The message buffer is a multi-set, so it can take on the same value multiple times. And when it and you can also ask the message buffer to receive a message for your process. So if you're process number 3 and you say message buffer receive 3, you're going to get important here, you're going to get a random message that is associated with P. So if you say receive 3, you're going to get a message that's addressed to 3, but it might be the most recent message sent. It might be a message that was sent a long time ago. You don't get to pick. The message buffer decides in a non-deterministic way, in this case, randomly, which message gets sent. The message buffer either does that, it either sends you a valid message, or it sends you null and doesn't change the buffer. And you don't know in advance what it's going to do. So this is, in essence, simulating a case where you might have to wait a while to receive your message. You might be calling receive 3, receive 3, receive 3, and keep getting null, 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 and eventually you do get a value. So the message system acts non-deterministically. If receive P is called infinitely many times, then eventually you will get all the messages, but the message system is allowed to return null as many times as it chooses, as long as that amount is finite. So the message system is non-deterministic. That's the thing to remember there. The processes, however, are totally deterministic. So the processes, each f of I, that is deterministic. That is guaranteed, or it's defined to be a transition function, but it doesn't change. It doesn't change based on its inputs. So if you have, given a set of inputs, the transition function should always return the same output. Synchronicity means what does the world in which our messages get sent look like? So as we saw, the message buffer is non-deterministic. That means we might get a message that when we call with CP, we might get a message right away. We might have to wait a little bit or even longer before we get the message. If we were talking about a synchronous distributed system, that would mean that we have an upper bound on the time that we're willing to wait for a message. We have effectively some kind of timeout or some kind of limit or step in which messages are allowed to be sent, and we refuse to wait any longer than that for our messages. So you might have like a timeout value. This, however, is not a world in which we get to be synchronous. As you remember from the abstract, we are looking at asynchronous processes, and the message buffer is not deterministic. So that means that we can't tell the difference between whether a process has failed or whether a process simply hasn't sent us a message. And then finally, failures. Distributed systems take on different kinds of assumptions about how, or I should say the definitions of distributed systems take on different kinds of assumptions about how they might fail. And that there are typically 4 different kinds of failures that you'll see in the literature. And from least severe to most severe, they are fail stop, which means your process just dies and refuses to send any more messages. But you can tell, perhaps, that it has done that. Like you can ask it, oh, are you still around? And it will tell you, oh, I'm not still around, or I'm dead. The crash means that the process simply stops responding and doesn't participate any further in the output of the system. Byzantine failures mean that, this comes from actually a different Lamport paper in which there's a story about generals that are trying to decide about how to attack a city, and they're Byzantine generals, just a historical artifact. But a Byzantine failure is where a malfunctioning process doesn't simply die or stop responding, but is allowed to send any message, including messages that are not valid. So it might, for example, send a message to a process that says, hey, self-destruct in 5 seconds, right? And then maybe that's not part of the protocol, but it may or may not do something. It might do something bad. It might disrupt the rest of the consensus, but anything could happen essentially with the Byzantine failure. Then permissionless Byzantine is sort of an even worse version of Byzantine. This is sort of like, imagine choosing difficulty levels in a video game. This is like the nightmare mode where essentially anybody can send anything and anybody can impersonate anyone. So it's really, really hard to have any kind of consistency or reliability in an environment that looks like that. But that's not what we're talking about today. We're talking about a world in which the failures are crash failures. All right, so to review the assumptions about the system, processes have that input-output register and the transition function and some kind of internal state. The system is specified entirely by the transition functions and the internals and the initial value of those input registers. Transition function is totally deterministic, so given some input, we're always going to get the same output. Message, from the synchronicity perspective, we're dealing with an asynchronous system. You might have to wait an unbounded amount of time for messages. Messages can arrive in any order. And the processes do not have any kind of access to a synchronized clock. There's no way they can tell how much time has passed. They just have to keep calling receive P on every clock tick or whatever. And importantly, that means we can't distinguish between a merely slow process and a completely dead process. So, and then a failure mode, like I said before, is based on crashes. So messages have an unbounded delay and processing time, and and because of that, there's no way to tell the difference between a slow process and a crash process. Okay, so to wrap up the first part of these definitions, the most important thing, and a definition that we'll refer back to a lot, is to kind of assemble all of those pieces together into what we call a system configuration. And the system configuration, or C in this case, or script C, is the combination of all of the internal states of each processor plus the state of the message buffer, whatever's in the message buffer at that time. And that's called the system configuration. So every time you see configuration or you hear the word configuration, that's what that is. It's some set of the states of the processors and the state of the message buffer at that moment in time. All right, how do we actually get to consensus, and what does that mean? A consensus requires something called TAV, and that means that given some P, that is, given some system specification, we would like the following properties to be true. We would like all non-faulty processes to be able to make a decision. They should all have something in their output buffer after some finite amount of time, or I should say eventually. We should have agreement. You can see where TAV comes from, termination, agreement, and the third one. We should have agreement, which means all deciding processes must make the same decision. So if you have something in your output buffer, it has to be the same thing as what everybody else has. And then finally, you have to have validity. So if you have something in your output buffer, it has to be something that was actually proposed by some other process. So if you never got a 0, you shouldn't see a 0 in your output buffer. Now, importantly, there are many, given some starting configurations, there are many possible paths you can take, right? The order of the messages you receive and that are sent and so on may determine many different results. And for some consensus algorithm, what we need to show, if this is a true consensus algorithm, it must have TAV for every possible execution. You have to be able to follow any path and arrive at termination, agreement, and validity. The way that the system changes state in the FLP paper is through steps. And that means that processes are calling receive P for themselves, and they get these events from the message buffer. So events are being received from the message buffer. They change the state of the system because the process applies its internal function, its internal transition function to update its state when it gets that message. So the system moves from one configuration to another through that step process, calling receive P and then moving to another internal state. So that means the only way that the system state can evolve is through this. It has to receive a message or possibly null from the message buffer. And so every step is essentially uniquely defined by the message that gets received and the process that receives it. So essentially every step is defined by the event that produced it. So that's what the paper calls those, is events. So configurations move from one step to the other through events. A run of events is called a schedule. So the set of, not the set, but the list of events as applied from one starting configuration produces a new configuration, and that list of events is called a schedule. So if you imagine all possible schedules for a given starting configuration, and then you think about if we could sort of peer into the future and look at what values are decided by that particular schedule, what are the values that get decided there, we will call that set V, the set of possible values that get decided from some starting configuration. If the number of possible values that can get decided is 1, the paper calls this univalent, but I find that term confusing, so we're going to call it decisive. It means you've arrived at a decision, everybody agrees, there's only one thing, and it's the same thing. So that's when the cardinality of the set of V is 1. There's only one thing in that set, and it's the same value for everybody, right? When there's more than one thing in that set, the paper calls this bivalent, a bivalent configuration, but we're going to call it indecisive. So just because bivalent and univalent sound like chemistry terms to me instead of computer science terms. So when the set of possible things is larger than 1, we can't decide because there's conflict about what the right answer is from that starting configuration. And if you might be wondering what happens if you have a value of 0, that you have a bad consensus algorithm there because it didn't wind up deciding anything. It did not meet TAV for at least one at the pass. It certainly didn't arrive at agreement, definitely didn't arrive at validity, and it looks like it hasn't terminated yet because it hasn't arrived at some conclusion. So we say that one of those execution runs, we say it's admissible when there's at most one faulty process. A faulty process is one that only takes a finite number of steps in that run. A healthy process can take infinite steps because it keeps calling receive P at some frequency or with some, it eventually keeps calling with CP. And so it's going to perform an infinite number of steps. A faulty process crashes and dies and can't perform any more steps. So a faulty process is one that only has a finite lifespan. We will say that a run is, an execution is deciding if there is some process that eventually decides using the consensus algorithm. And we say that the algorithm is totally correct if every admissible run, if every run that contains at most one faulty process also decides a value. So if that's true, then we have total correctness for our consensus algorithm. And that would be ideal. That would be the case we'd want. So the FLP Impossibility paper has 3 lemmas using this definition. Now we're actually getting to past the definition part of the paper, which, as you can see, was quite substantive. So the FLP Impossibility proof has 3 lemmas to it. And if you look at the actual wording of the paper, the most time is spent on lemma 2, a little bit of time is spent on 1, and then very little time is spent on 3, even though 3 is actually one of the most important pieces of the paper. So I'm going to try to smooth that out a little bit more and try to spend what I think is the appropriate amount of time on each of those instead. So the first lemma is that disjoint schedules commute. What does that mean? If you're familiar with sort of the multiplication version of commutativity, that means that if you have 4 times 3, that's the same as doing 3 times 4, right? Both of those values are equal. They're equal to 12. And if we have 2 schedules, if you apply 2 schedules in the same order, 2 schedules in different orders, and they're disjoint, meaning they apply to different sets of processes, then we'll wind up in the same configuration no matter what order we happen to apply them to. So if you have, say, S1 and S2, and they're disjoint, then following S1 from some initial configuration takes you to some other configuration, C prime, and then following S2 from there takes you to some final configuration. Following S2 from the initial configuration takes you to some different middle configuration, C double prime, and then following S1 gets you back to there. You can imagine a sequence of like light switches, and if there are, say, 5 light switches on the wall, and I say flip 1 and 3, that's instruction set 1. When I say flip 2 and 4, and that's instruction set 2, those are disjoint instructions. They don't apply to the same set of switches. And so if I do the first set of instructions and then the second set of instructions, I get one result. And if I flip the ordering, I get the same result. So even though I applied the instructions in a different order, I still wound up in the same configuration. Same idea here. All right, lemma 2, second lemma, is that some initial configuration is what the paper calls bivalent and what we'll call indecisive. So there's some initial configuration of values that does not decide an answer. So the way to arrive at this conclusion is suppose that every initial configuration was decisive. So every initial configuration, no matter what path you take from that initial configuration, it leads to either all zeros or all ones. That would be a decisive configuration. So if you have n processes, then there are 2 to the n possible initial configurations. And if you can arrange these 2 to the n initial configurations such that any 2 adjacent configurations differ by at most 1 process. If you arrange them into a lattice, for example, you would see that. If you had, say, 4 processes, then you have 2 to the n initial, if you have 2 processes, then you have 2 to the n initial configurations. You can imagine a square in which the lower left corner is 0, 0 initial configuration, 0, 1, 1, 0, and then 1, 1. So if you imagine arranging that onto a lattice, any 2 points that are connected to each other in that lattice differ by at most one process in the initial configuration. So we do that ordering. So that means that somewhere in that lattice there will be a configuration that differs by only 1 process, right? And remember that we said here all initial configurations are decisive, so we must have there must be some configuration that decides a 0, and there must be some configuration that decides 1. And so we have some number of zeros and some number of ones, and eventually we'll have a 0 and a 1 that are right next to each other. And because they're right next to each other, they must differ by only 1 process. And that means that there must be something is different about these 2 runs because they decide different values, but they differ by only 1 process. So let's say that differing process is the one that crashes. So we have an admissible run, right? An admissible run lets us crash one process. Suppose that's the process that crashes. Well, that means that we are supposed to arrive in some state, and the only thing different between this configuration on the left and the configuration on the right is what happened to P, right? So P crashed. That means that P didn't participate in any of the, it couldn't send or receive messages. It wasn't part of the system. But yet somehow we wound up with a case where P is supposed to have caused a difference because these two values are different. So we decided different values even though P crashed. So that's a contradiction. P caused a difference, but we said earlier that the system should only be able to depend on the initial state and the transition function. So P crashes, we know what its initial state is when it crashes, but we arrived at a different result. So P shouldn't have been able to cause a difference, but it did cause a difference. So we got an undecided configuration. So that's a problem. And so that means that there's at least one initial configuration that is that's indecisive, that is, or bivalent in the paper's terms. All right, so the third lemma is that no matter what path you pick, no matter how you get to the, no matter what path you take to the, I think I just got the red ring of death on my computer because the power light flashed orange. I've never seen that before.
Uh-oh.
Okay. And we'll see if restarting it helps.
Do you get it out of juice?
Yeah, I don't think so. There's not out of juice. I just charged it before I left. Well, you know what? There's not that much left. Why don't I just see if we can wing it from here? Because I don't think this is going to boot back up. I just tried it, and yeah, I think it might be dead. Pivotal might be getting me a new laptop. We'll see.
Okay. We can get a laptop if you have to slide somewhere else.
I do, but I feel like that would almost take more time to figure that out. Like, okay.
You're the boss.
Sorry. All right, so that third lemma is that all roads lead to indecision. That is, no matter what starting configuration you have, and again, this is the one that I feel like the paper doesn't really spend that much time on because maybe it's particularly dense. Unfortunately, the diagrams would have helped most at this point. But basically, if you start from an indecisive configuration, if you start from one of those C's that was indecisive, remember we had the 0 and the 1 right next to each other? So if you start from one of those configurations, that's a indecisive configuration because both of them, you should have had a 0 and a 1, but we wound up at a state where you could have either, even though there was a process that crashed. So if you start from there, informally what this lemma says is that if a protocol starts from an indecisive configuration and there's some message, some event E that is applicable to that configuration, then there is a set of configurations that's reachable through any sequence of messages where E was applied. And where that was applied, that contains a indecisive configuration. So going back to the light switches example, what that essentially says is that there's a way to flip those. There's a set of messages about flipping light switches such that the rule about how to get to all zeros or all ones on those light switches might cause me to, depending on what initial configuration I start with, it's possible to have some message that makes the difference between whether I wind up in an indecisive configuration or a decisive configuration. So what that really says in a more sort of intuitive way, without using the language of the paper, is that if you delay a message from one event to many events, so if there's some message E that you're supposed to have received, but the message buffer just keeps telling you null, null, null. So you're doing receive 3, and there's a message with 3 in the buffer. It's for you, but the message buffer decides, for whatever reason, I'm just going to not give you that message right now. Then it's possible to wind up in a configuration where you do receive the message, but you wind up in a bivalent / indecisive state. So that ingredient in the proof means that if you guarantee that there's a path from one indecisive configuration to another indecisive configuration only by delaying a message long enough, then that means you can construct a case where there's always going to be some way to delay the message long enough such that you go from indecisive to indecisive. And And those three lemmas taken together form the bulk of the proof. If you can imagine a execution in which a message keeps getting delayed, you can construct an execution like that, then what happens is the message keeps getting delayed, it never gets delivered, and by the third lemma, there's no way to arrive at a decisive state. We keep going from one indecisive state to another indecisive state to another indecisive state by delaying that message over and over and over again. So because of that property, that means that it's always possible to construct an infinite sequence of infinite indecisive states. And that means that you'll never or possibly never arrive at a state where you can achieve consensus. And because we assume that because an admissible run was one that had at most one faulty process, that means that there is no way to construct a distributed consensus algorithm that applies to all possible configurations such that you can never wind up in an indecisive state. But there is some amount of hope. And the way that we can get back to the good place is to make a few more assumptions about our systems. So we saw that one of the assumptions we made earlier was about synchronicity, right? About the fact that this is an asynchronous system. And specifically, we defined an asynchronous system to be one where the message wait is unbounded. You might have to wait an theoretically infinite amount of time, and you can't tell the difference between a crash process and one that's just really slow. But real-world systems don't quite work like that. Like you will refresh your browser after 10 seconds. You will retry some message after a timeout. You won't wait an infinite amount of time. So real-world distributed systems can do things a little bit differently. They don't have to abide by that specific restriction. And future papers after FLP explored what happens if you start relaxing some of these assumptions. Like, okay, it would be nice if we could sort of guarantee reliability in this very, very strong version of consensus. But what if we're okay with like timing out? And what if we're okay with dropping a message if it doesn't get there quick enough, that sort of thing? And that's sort of how we get around this problem. Like, because obviously we do have distributed consensus algorithms that work in the presence of faulty processes. So there must be something different about the assumptions they make than the assumptions the paper makes. So let's take Raft as an example. How many people are familiar with Raft? Oh, wow, wait. Okay, I guess I should have expected that for people attending a paper and self-selecting into a talk about distributed systems. Okay, so you probably know that Raft is it's a distributed consensus algorithm. It's a way of deciding on those zeros or ones, right? And the interesting thing about Raft is that it makes an assumption that it's not going to wait more than a certain amount of time to hear from its peers, and that's called the election timeout. So if it doesn't hear back from other processes quickly enough, it's going to assume that, the way that we're trying to agree on things is no longer valid. We have to figure out who the new leader of our Raft cluster is, and we're going to have to start a new election. So that's a case where a specific case where a distributed consensus algorithm does not follow the rules as laid out by the FLP paper. So it's asynchronous in that it's synchronous in that it bounds the amount of time it's willing to wait for a particular message. Okay, so there is sort of hope, right? So that's sort of the first way out. Is what if we relax the definition of our system, of our consensus, so that we can try new things or try different things? And that's the most common way that it gets relaxed is through synchronicity. The other common way that you start seeing things is through the form of failure detectors. And failure detectors were a separate sort of branch off of the FLP paper where we started thinking about, well, what if you didn't have to accept that a process was simply slow versus crash? What if there was a way to tell that a process was going rogue or getting crashy, right? And how much would you need to strengthen the asynchronous model in order to allow for consensus? And so there are different papers that explore different angles in which you can try that. So that's another angle that people try to chip away at the FLP paper. But nevertheless, in that world where you have at most one faulty process and you accept those assumptions, you can't have distributed consensus. You can't have a distributed consensus algorithm that decides all those things. The last point I want to make is that remember that we have to remember that all the FLP result says is not that you're guaranteed to wind up in a state where you have an infinite indecisive run, but simply that it's possible to wind up in such a state. And so the analogy might be, if you imagine throwing darts at a dartboard, what's the probability that you will throw a dart that lands exactly in the center of the dartboard? Well, it's not 0. One of those points is in the center of the dartboard, but there are an infinite number of points on the dartboard. So it's not 0, but it's also not it's also not all the time that you will hit the dartboard. It's sort of all the time minus that one very special case where you don't. And so if your distributed consensus algorithm is okay with a probabilistically converging to one notion of consensus, then you're actually okay, right? Because you can decide, well, I don't need it to work all the time. I just need to be able to try it enough times, and eventually I'll win because the probability of getting into a bad state is very small. So this is the approach that blockchains take, which if you saw my last talk, that's what we talked about. So blockchains require, in order to work, they require consensus. They need enough of the network to agree about what's going in a transaction, what's in that block, who's getting paid by whom, et cetera, et cetera. And if you don't have that consensus, blockchains don't work. So how do blockchains make it work? Well, they make it work by just keep trying until you get consensus. So just keep waiting enough and you'll get consensus. Sometimes if you don't wait long enough, that consensus gets reversed and is broken, so you didn't really have consensus, right? But you can't tell whether you really do or don't have consensus. You just have to be willing to wait long enough to weed out any, to accept some lower error bound on how bad things might be. So those are the three ways in which we sort of escaped the FLP conclusion and kind of gotten back to the good place with distributed consensus algorithms. If we're willing to relax those assumptions, then we can get back to the good place. Unfortunately, because because relaxing those assumptions also means that we have to deal with more complex systems, right? We have to build things that are more complex than we otherwise might have to, because the FLP result is really about a very, very strict notion of how those processes work. So when you relax those assumptions, you're inviting more complexity and weaker forms of consensus that may or may not handle all the use cases you'd like them to. So if I could give you three takeaways from the talk, I would say one is that the FLP paper really marked a seminal change in the way that we thought about distributed systems, in the way that not just in terms of the assumptions we made about the reliability, but also in terms of how we designed and constructed them. So people stopped, for example, there was a very noticeable difference in the claims that vendors were making about the reliability of your systems in 1982 than they were in 1984, right? Because you're going to look pretty silly if you claim reliability on something that's been mathematically proven to be false. It's kind of like, database vendors will be totally happy to claim things about the reliability of your database right up until they get Jepsoned, and then, whoops, it turns out that all those claims were not actually true. So that's sort of the first takeaway. The second takeaway is if you're willing to relax those assumptions, if you're willing to relax the FLP assumptions, you can still get usable and valid and useful distributed consensus systems. They're just not quite as strict or rigorous as the ones that are laid out in the paper. But that's okay, because the real world doesn't necessarily look like the one that's in the FLP paper, right? It's very possible to construct mathematical structures that have no bearing in reality. Some might say that's the job of a mathematician, to sort of explore those crazy spaces and say, how do all these things fit together? What are the abstractions that are interesting or useful? And then see which of those happen to turn into a useful result, right? Like all models are wrong and some are useful, kind of a story there. And then the third thing I'd say is I think the paper is interesting because of the, sort of taking the first 2 points together, I think the paper is interesting because not just that it caused a sea change in how we think about things, but also that the ripple effects are still true today. Like if you want to design a distributed consensus system, nobody's proved the paper wrong or found an error in that proof. And as far as we can tell, it's totally correct if you accept all the premises. So that means that if you're a distributed systems designer or you're interested in designing distributed systems, you have to essentially read this paper to understand how to do your job. And I think that's rarely true elsewhere. I mean, even in software engineering, I feel like some of the questions I may have answered on Stack Overflow are essentially, why can't I do this thing that's equal to solving the halting problem, or something like that? But I wouldn't say that reading the halting problem paper is a prerequisite for software engineering. But I might say that reading the FLP paper is probably a prerequisite for doing a good job in distributed systems. So that's everything I had to say. I hope you enjoyed the 60% of a talk that actually had a screen attached to it. So thank you for sticking with me through the technical difficulties, and I'll be glad to take any questions.
Thank you so much. I'm going to take presenters' discretion here. I'm going to ask a question first. How does this relate to CAP theorem?
How did what?
How does this relate to CAP theorem?
In terms of FLP? Or
yeah, is this sort of this sort of proving the network leg of CAP theorem?
Yeah, so I would say you could sort of imagine a distributed system of databases as processes that have a transition function. The difference between the CAP theorem versus FLP is really about the system as a whole, and CAP is really about the context of transactions and the relationships between the messages. And FLP doesn't really, in fact, it relies on the fact that messages can be in any specific order as a condition of the proof. CAP theorem is really more about the structure and the relationship of those messages to each other. So they're related in the sense that they both describe an idea about distributed systems, but I think they're quite different in the sort of the assumptions they make about the system in order to prove that CAP might be true.
The methods they're talking about. Okay.
Yeah.
Just wondering.
So it's the sort of mathematician idea about, like, I would argue the CAP theorem, the assumptions the CAP paper makes are much more in line with what systems look like than the FLP paper. So.
Other questions? We have one here. Wait for the mic to come to you. I think we got one coming behind you there.
Thank you. I'm curious how central the assumption is that messages are delivered out of order, because it seems like ordering messages is a
What does order mean?
Reasonably well. So if a process sends one message and then another, the recipient will not receive them in the opposite order at any time.
So from the process's perspective, if it sends message 57 and then sends message 58 to the same process or to two different processes?
To the same recipient.
Okay, so if the same recipient gets two messages, it should receive those messages in the order that
the sender sent
originating process sent them? Yeah, I see. How central is that assumption? If you take away that assumption, I think that you would have to be, I think that would require you to reconstruct the third lemma, because you'd have to be able to show somehow that you could still sort of remove and delay some message, and it could no longer be any message. It would have to be, I guess, the last message in that ordering. So you'd have to be able to show that you would still wind up with lemma 3 without the message. I don't know if that's possible or not, or if that disrupts the whole proof. But that's essentially, that would be the impact of changing that assumption.
Thanks.
Sure.
Other questions? We have one back here.
Hey, so towards the end of the talk, when you're talking about how kind of real-world systems get past this result, you kind of you divided the directions in which they go into two. You said that some systems use failure detectors, others use timeouts, and then blockchain does its own thing.
Right.
Is there really a difference between the first two? Isn't a timeout? What is the difference between?
Yeah, sure. I would say failure detection is sort of a more general case of timeout. Timeout is specifically waiting for X amount of time. I don't hear anything. It's broken. Failure detector could do any number of things, including timeout. It could be something like, I'm going to poll you, and if you don't return the correct value, I'm going to assume that you're in a bad state, so I'm not going to talk to you anymore. Failure detection involves depending on how you define it, it involves a superset of timeouts. But I would say at the time the FLP paper was being explored, they were much more synonymous. Like failure detection was using timeouts, if that makes sense. As I understand it, as the literature developed from the FLP paper, there was more consideration around, well, what does it mean to be not timing out, but still in a bad state? Like what if you return messages, but you're returning the wrong messages or bad messages, like you're in a Byzantine failure mode, for example. Can you do failure detection in a world like that? Can you do failure detection in a world where you have permissionless Byzantine? Can you detect that people are forging messages that don't really come from them? Is there a way to check that? The FLP paper doesn't have anything to say about that because it assumes about crash processes. Actually, that's not true. It talks a little bit about Byzantine failures, but it's pretty much just about crash processes. But successive papers explored what happens when you have failure detection in a permissionless Byzantine world, but what if you have messages that are unforgeable? Are those two assumptions incompatible, or can you still wind up with a situation like that? So does that answer your question? But sort of failure detection at the time was about the same thing as timeouts, but as time has gone on, it's encompassed a broader set of capabilities.
I think we may have had a talk on failure detection as well recently. So I need to go check. I don't have memory for that.
Yep.
Wait, a question up here.
So you were talking about blockchains as solving this by sort of try again until they get a result.
That's a gross oversimplification, but
I was going to say that I think of it more as that they're not as deterministic as these processes are. Like it doesn't really necessarily matter that they always get the same result, or that in every possible universe they would get the same result as long as they come to some result. You know, there's a statement
matter.
here.
Say that again. It doesn't matter that.
So there's an assumption in this paper that each of these processes is deterministic, even if the message buffer isn't. And I would say
the message buffer is not deterministic.
Right, but the processes are.
Yes, right.
But whereas a node in a blockchain might be less deterministic because there are.
Well, I would say a node in a blockchain is deterministic. If you're not all following the same protocol, when you're not obeying the same rules, and so you're not going to arrive at the same answer about what it means to have consensus.
The kind of example I'm thinking of is that sometimes the order of events that will say, like in Bitcoin, it might be that one miner is picking one order and another miner is picking another order, and there can be like random factors that influence that.
Well, so the order in which the messages arrive, if they change, then that's different input. But if they arrived in the same order, you would expect the node to.
I'm saying I wouldn't.
You're saying you would not.
I would not.
Are we talking about a specific blockchain?
I know that
I should say.
I know that miners, it's up to their discretion which transactions to put into a Bitcoin thing. But I know also that there's other ones like Ripple and Stellar where there's a validation process that puts things into orders. It has these orderings that can depend on other factors that have come in, like the hashes of signatures.
Let's just take Bitcoin as an example.
Yeah.
If you have a set of transactions, I mean, we're going back to the first paper. Oops. What? Is that still on me? Yes. Okay. Sorry. So let's take Bitcoin as an example. You have a set of transactions in a transaction pool that you would like to turn into a block. You can only fit so many transactions in that block. So are you saying that the non-deterministic part is which transactions do you take from the pool and put into your next block that you're going to publish as a miner?
I know that with Bitcoin, that's up to the discretion of the miner. You could choose to have no transactions in a block.
Right. So I would argue that something that's up to your discretion is a human being doing something that's not part of the transition function, if you will. Like if there was a rule about always pick the top 5 transactions and stuff those into the next block, and you wrote that down in software, that's the rule. That's part of the transition function. If what you're saying is, well, actually the rule is defer to Bob, the human being who's going to pick the transactions, I would argue that that's deterministic in the sense of the rule is always defer to Bob, but what Bob picks might be different from one case to the other. So in that case, you wouldn't have a you wouldn't have a transition function that was deterministic, if that's what you mean.
It sounds like a talk about it after the bar
I
question
agree.
too. It sounds like a rabbit hole to me.
Thanks for that.
We going over here?
So is Lemma 3 saying that the message can get potentially delayed infinitely, or that you can delay enough to at a certain point, if it does arrive, it's so far out of order that the consensus is broken?
So it's not so much about being, quote, out of order as it is that, I'm stating it informally. It would be really nice if I had the diagrams. But essentially, if you, so there's some pending message that you would like to deliver. It's in the message buffer. And remember, the message buffer might or might not delay your message by 0 to some possibly very large number of times before you get that message. What Lemma 3 says is that if you delay that message from any amount from a single event to some very large number of events, then there is some configuration in which you eventually receive that message, but nevertheless wind up in a indecisive configuration, a bivalent state. So that, and the way that you, and the reason that that's important to the proof is that if it's possible to do that, if you can, remember we know from Lemma 2 that you always start out with a indecisive state. And Lemma 3 says it's possible to delay some message somewhere such that you wind up in another indecisive state. And then it's possible to do that again, and then again, and then again. And so the proof is, here's how to construct such a run that's admissible, but yet winds up in an indecisive state. Therefore, there's no way to have a consensus protocol that arrives at a state that it decides a value for all possible values.
And so the fact that in Lemma 1 it says that operations commute, even though they can commute if it comes out of order, that doesn't really factor in it. There's still configuration.
Remember, Lemma 1 only applies for disjoint
Okay.
messages. So if you have like the same message, the same process receiving a bunch of messages, that's not disjoint. Because it would have to be like light switch 1 and light switch 3 versus light switch 2 and light switch 4, not light switch 1 37 times interposed with light switch 3 some amount of times. Like you'd wind up in a different state there.
Okay, that makes more sense.
Yeah.
Any other questions? They're all good. So I'll go right next to you there.
This is actually just more a historical question.
Sure.
You were laughing about, when this paper came out, 1984 would have had to have very different marketing messages. This is just my ignorance. I entered the industry in the mid-90s, so I actually didn't see a lot of folks doing strict consensus algorithms, and I'm thinking Paxos-based algorithms, really until things like the Zookeeper atomic broadcast came out, and not that that's Paxos, but Zab or Ceph and things like that. Do you have any historical systems that were actually trying to follow some of these consensus algorithms in that era? Like, I don't know if Wang maybe did, or...
So sorry, the question is, are there, sorry, repeat the question again.
Yeah, just are there historical systems that you know of, commercial systems perhaps, or otherwise documented, that were using distributed consensus protocols, distributed decision processes back
That's a good
then?
question. I don't know of specific systems that were, I know that there were, like, for example, various early databases that were, doing what at the time they would have called replication, but now we would say is more like failover. So like database 1, database 2, database 3, one dies, you switch to 2, and then there's some thing that happens where 2 gets all the missing records or whatever. So they were using, these vendors were making the claim that they were doing consensus around that because, well, the system as a whole, like, you don't know which database in a cluster is giving you the actual records at any given time, but no matter who you asked, you would wind up with the same answer. So some kind of eventual consistency. I don't know of any specific systems that I could point to that were using specific distributed consensus algorithms. Sorry.
That's cool.
Does anyone know when the Raft paper was published?
pretty recently.
Oh, that's recent. Okay.
After 2000.
Oh,
right?
okay. I thought it was older than that.
No. Yeah, I think Raft has been in the last like 10 or 15 years. or so.
2010. Oh, okay. Oh, we have is someone in the back? Just yell it out. Oh, go ahead. Yeah.
Yeah, hi. Can you say a few words about different notions of consensus? So the weakest notion of agreement or consensus and the strongest one, kind of the scale of,
Like, what is it?
Well, what is the weakest notion of consensus that you can
I mean, the
think
weakest
of?
notion of consensus would be something like the only way that things can fail is in this very limited way, or like processes never fail. I guess that would be a very weak form of consensus. Like everything always works all the time. How do you arrive at agreement between processes? So most people find that not useful because processes do crash in the real world. So that's probably the weakest you could get right before it stops being actually useful, right? Because if you say, well, this only works if processes never crash, like I don't know if many people would be willing to accept that assumption.
You're saying you're imposing very strong condition on the system, so consensus is weak, but the system is so.
Well, I mean, that is a form of consensus. Like, if you're talking about like the weakest possible, I would say that's the weakest possible. Processes don't fail, right? I think that's so weak that no one would really. If you published a paper that was like, I have this amazing super performant algorithm, it assumes that nothing ever dies. Like, how useful is that in practice? I don't know. Like,
the confusion is weak means limited utility.
oh, I see. So do you mean weak? Yeah, I guess. Do you mean weak in the sense of very few assumptions?
I mean,
So I would say a strong result is one that applies to lots of use cases. I would say a weak result is one that applies to very few or very limited, sort of almost degenerate cases, right? So a weak consensus, a weak distributed consensus algorithm, or I should say a distributed consensus algorithm that makes weak assumptions would be one that says, well, let's assume that processes never crash. A strong one would be processes can crash in any way possible, they could forge their messages, and by the way, we still have consensus somehow. Like that would be a very strong. This is sort of in between those two. This is processes can crash, but they can't send messages that they don't want to or are not supposed to. So we can't like interfere with the consensus that's emerging from the processes. Does that answer your question? Okay. Sure, I'd be happy to talk to you afterwards if you want to.
Historical
would show you
example
something
of a
that might
consensus
use it,
protocol
yeah.
that was used in the wild is AppleTalk from the early to mid 80s.
Say that again, I'm sorry.
AppleTalk is a distributed consensus protocol that was used in the early 80s.
Oh, okay. Well, there you go. That answers your question, I think. Yeah.
And it's better when thinking about the history of this to think about Paxos rather than Raft, which is from '89.
That's what I was thinking.
The other thing is it was kind of I was really young back then, so I kind of learned this from history books, but consensus became and distributed systems became more interesting later on because the systems from the 80s that you tended to run databases on were really expensive and rarely failed. Tandem systems that were started back then are, I think, still running literally today. It just doesn't come up that often when you don't crash. It's kind of a Google thing when it's like, let's throw a bunch of cheap computers at the problem, and then you start really caring about it.
Fair point. You have a question up here.
Oh, sorry. Over there. Oh, sorry. I saw the microphone being handed to that guy, so I thought it was you.
Yeah, you mentioned before the set of configurations which forms a schedule can be represented as a lattice. Is that correct?
So the initial set of configurations, I think you're talking about how do we show that, the second lemma, how do we show that you always have a indecisive configuration that you're starting from?
No, I'm talking about the system representation. You said that initially you can have a set of configurations, and then that would form a schedule. And you said that if you represent that, it could be a lattice. Mathematically,
What I said is if you have n processes, then there are 2 to the n possible starting configurations because they can have 0 or 1 in their initial value, right?
So you're saying that system state can be represented as a lattice. Is that what you're saying?
The set of possible initial configurations can be represented as a lattice.
So what would be the ordering relationship?
Just imagine that the ordering of the processes. So imagine a lattice starts at, in the case where you have two processes, right? And there's 2 to the n, which is 2 to the 2, right? So the ordering would be 0, 0, 0, 1, 1, 0, 1, 1.
So the values are order, is that what you're saying? The values, the consensus algorithm design are order?
So there are 4 tuples there. There are 4 2 tuples. Each element in a tuple is the initial value of that process. So in, say, the 1, 0 tuple, the second process has initial value 0. In the 0, 1 tuple, the second process has initial value 1, first process has initial value 0.
Right, but how do you order the tuples?
It doesn't matter how you order them. It just matters that, for example, in a lattice, it just matters that whatever ordering there is, there's always going to be a case where you have a 1 next to a 0. You're always going to have a 0 deciding initial configuration and a 1 deciding configuration next to each other. There's no way to arrange the lattice such that that doesn't happen.
Yeah, but that would depend in the 0 and 1 are, like, 0 and 1 can be just 2 extreme values, right? So
But remember,
this depends that the values are order.
think about like the pigeonhole principle, right? You can only have 0 or 1. Those are the only 2 deciding values. You've got 4 slots to put those in. You're going to have a 0 and a 1 next to each other somewhere. So by the pigeonhole principle, you're definitely going to have a way. The ordering just gives you a way to pick which of the values it is. You're always going to have a 0 and a 1 next to each other because of pigeonhole principle. The lattice ordering stuff is just, here's how you get that ordering. Here's the specific way to do it. And the specific way to do it in the papers example is use a lattice, radix sort, if you will, the tuple so that, every 0 comes before a 1, and then look up a leftmost one first, then the rightmost one, or then the next right one, and the next right one, and the next right one, and so on. Does that make sense? If you imagine them as strings of binary digits, order them that way.
Oh, okay.
Yeah.
All right. I think we'll take the last one right here, and then I think we'll wrap up for questions. Right here. Right.
All right, I got a dumb question. So the proof
sure
here
there are
deals
no
with
dumb
just
questions.
these 2 Boolean values, 1 or 0. Obviously, computers are slightly better than that. We have numbers, exciting
Right.
numbers such as 3 and 2, 4, and so is the idea if we can't get this to work with this simple binary choice, then we have no hope of possibly getting it, processed to agree when we have a bigger alphabet? Is
Right.
that formalized within the proof, or is it just kind of taken for granted?
Well, I would say that's a very strong assumption in essence. Hey, it doesn't work with 2. It's definitely not going to work with 47, right? Because then what you'd have is a case where that lattice, if you arrange it in a lattice, instead of being 2 to the n, it's 47 to the n, right? And then that means that not only are you going to have way more configurations that are next to each other that only differ by 1 instead of at least 1, right? So you're going to have probably 40, probably 46. There will probably be some configuration in there that differs from 46 other configurations next to it by at most 1 process in a world where the alphabet was the size 47.
And if you can picture a 47-dimension lattice in your head, please call MIT. I think we'll wrap it up there. We will be at the bar later for more conversation. Thank you so much.
Thank you for having me.